Hey guys, Mr. L coming back at you with another video. And in this video, we're going to talk about the shape of an overall larger particle that may have more than one central atom. We're going to talk about the polarity of larger particles, not just the polarity of bonds, but the overall particle itself. We're going to talk about the hybridization or mixing of atomic orbitals on central atoms for organic compounds and some other inorganic compounds, as well as we're going to talk about the difference between sigma and pi bonds. So let's get into this video. So the first thing we're going to talk about is the shape of an overall larger particle that may have more than one central atom. In this case, what you're going to do is you're going to try and treat each atom that has connections or lone pairs to it as a central atom and just move further down the chain. So in this example, I've built a model here. So let me get a little closer. And we've built a model of ethanol. So ethanol has multiple central atoms. We can rotate this 360 degrees, and we've got three central atoms. We've got the oxygen, the central carbon, and then the outermost carbon. And all we're going to do to see the overall shape of this thing is we're going to look at each central atom independently. So first, let's look at the oxygen. Oxygen has 4 domains total, 2 bonding domains, and 2 domains that are in this empty area. They're not really empty, but they're shown as empty. And we're going to have 2 sets of lone pairs here. So this would overall be tetrahedral in shape with a bond angle of slightly less than 109.5 because we've got some squeezing due to that lone pair mass at the top. So this is going to be tetrahedral bent with a less than 109.5 degree bond angle. The central carbon atom here has 4 domains, 4 of which are bonding domains. So again, this is going to be tetrahedral, and we don't have any lone pairs or double bonds squishing this in any direction. So this would be tetrahedral with a 109.5 degree bond angle. And then lastly, this outer carbon also has 4 bonding domains, no lone pairs. So this would be tetrahedral, 109.5. So each of these individual central atoms gives the overall shape of ethanol. Let's look at another example. Here we've got propene. So we've got a double bond here, and we've got a prop chain, 3 carbons. Looking at this outermost carbon on this side, it's very similar to the ethanol that we had. We've got 4 domains, all bonding domains. So this would be tetrahedral, 109.5 degree bond angle. The central carbon here has 3 domains, 3 bonding domains. Even a double bond here is counting as 1 bonding domain. So we've got 3 bonding domains, no non-bonding domains. Therefore, this is going to be trigonoplanar in shape with an approximate 120 degree bond angle. And then the outermost carbon here, again, has 3 bonding domains, no non-bonding domains. So it's going to be trigonoplanar as well with an approximate 120 degree bond angle. What's going to happen due to that double bond, though, is you're going to have some squeezing on the outer areas here, causing this to be slightly less than 120 in between these angles here. And then we've got slightly greater than 120 at these angles with the double bond due to that extra space occupied by the double bond. So now let's start to talk about the polarity of overall particles now that we have an idea of visualization of a larger particle. So we talked about before that we have polar bonds between 2 atoms, such as our ethanol particle. Our ethanol particle has an oxygen-hydrogen bond, which is very polar. So we've got a polar bond within this particle. We have a long hydrocarbon chain, which is going to be generally nonpolar. Because this is not equal and opposite poling on either side, we're going to have an overall dipole or a partial negative towards this oxygen area, and then we're going to have some positive pole coming towards this other hydrogen area. So this is going to be a polar particle. It's not all nonpolar. Another 2 examples of this would be something like carbon dioxide. Carbon dioxide has polar bonds. There is a difference in electronegativity between the carbon and the oxygen. But the thing to notice here is that this is a linear particle and our vectors are going equal and opposite directions, so our vectors are canceling out, and carbon dioxide is overall non-polar. Even though it has polar bonds, they're equal and opposite. If we compared that to something like water, water is a polar particle. It's got polar bonds between the oxygen and hydrogen. It's got lone pairs over the oxygen, so oxygen is going to be partially negative, and between the two hydrogens is going to be partially positive. So determining the polarity of an overall particle, you got to think about the bonds as well as the directionality of these vectors of the polarity. So let's tie in some previous knowledge that we learned in a previous video, and that's the idea of valence bond theory, or covalent bonds are going to form between valence electrons of separate atoms, and they're going to share those electrons to form a covalent bond. So in something like diatomic hydrogen, it's forming a covalent bond by overlapping their 1s electron clouds. So you're going to have an overlap of the 1s of one hydrogen and the 1s of another hydrogen, and that's what's going to form a covalent bond. If we have something like hydrochloric acid is going to form a covalent bond between the 1s cloud of hydrogen and the 3p cloud, which is the empty suborbital on chlorine, and that's what's going to form a covalent bond. And then something like diatomic chlorine, you're going to have an overlap of the 3p electrons for both of these. So if we were to look at this energy schematic versus distance, the overall covalent bond distance is going to be dictated on the attractions and repulsions between the two atoms. You're going to have an optimal bond length depending on those repulsions and attractions. If you squeeze the atoms too close together, they're going to want to repel past each other, so the energy value is going to go up. And the opposite is true, is if we start pulling these two atoms further and further together apart, they're going to want to come back together to form that specific bond length. So at the bottom of the energy well, this is where we're going to form our covalent bond length. So now let's talk about the idea of hybrid orbitals. What a hybrid orbital is when we mix two or more orbitals that have different energy values, and then the output is the two or more degenerate energy values. And remember, once again, degenerate in chemistry and physics means equal in energy. So we're going to put in two orbitals, like an s and a p orbital. They're going to be slightly different energy values. We're going to mix them together, and we're going to get an output of an sp hybrid orbital with equal energy values. And this is supported by what we see in nature. If we were to look at something like methane, CH4, we could see carbon typically takes 4 bonds. But if we were to look at the electron configuration notation of carbon, it would be 1s2, 2s2, 2p2. We would only have 2 spots available for bonding in the 2p orbital, so something must be happening. Well, what's happening is hybridization. We're going to promote 1 electron from the 2s orbital and move it over to the empty p spot, and now we've got 4 empty slots for bonding. But it doesn't really make sense to have a lower energy s value and 3 higher energy p values. So what we're going to do is we're going to mix all together our 1s and our 3 sub p orbitals for a total of 4, and then our output is going to be called an sp3 hybrid, where we've got 4 empty spots, each with 1 electron available for bonding, and they're all equal in energy. So this is called hybridization. We're going to mix our s and our p orbitals up, get equivalent energy values, and spit back out equal energy values, each with 1 electron available for bonding. So let's try to think about what the sp hybrid orbital is going to look like. The s orbital was sphere shape, and p orbital was the dumbbell infinity sign. If we were to mix these two shapes together, you kind of get like that childish goldfish, or when you were 3 years old and you first learned how to draw a fish, where you draw the big head and then a squiggly little tail. It kind of looks like that, where it's going to have some spherical shape due to the s orbital, but it's going to have a little dumbbell lobe on the other side due to the p orbital. So I like to just say it's like a fish shape, or the little kid goldfish cracker shape. So there are 3 major categories of sp hybridization. And that's what we're mostly going to focus on in general chemistry and AP chemistry, are sp hybrids. There are other hybridizations that can occur, but we're going to focus on these. So there are 3 major categories. The first one, such as in beryllium difluoride, we have an sp hybrid, where you're mixing 1 s orbital and 1 p orbital together to get an sp hybrid orbital. We have sp2 hybrid, where we're mixing one s orbital and two p orbitals together to get three sp2 hybrid orbitals out, such as in boron trifluoride. And then the last category is an sp3 hybrid, where we've got one s and three p orbitals all mixing together to get out four sp3 hybrids, such as in methane or ammonia. So the easiest way to determine the hybridization, if you've got like a Lewis diagram, is take the number of domains and subtract 1, and that should get you to the hybridization. So if we have something like this ethanol again, if we're looking at the hybridization on this last carbon, it's got 4 domains on this final carbon here. If we subtract 1, therefore we should have an sp3 hybrid. We have an sp3 hybrid on this end location here. If we're looking at the oxygen, it's also an sp3 hybrid. It's got 2 bonding domains, 2 sets of lone pairs, which are in this empty space up here, for a total of 4 domains. So it is also an sp3 hybrid. Let's look at now propene. This N carbon with the double bond on it in propene is an sp2 hybrid because we've got 3 domains, and if we subtract 1 from that, that's 2. So this is an sp2 hybrid. So we've got 3 sp2 hybrid orbitals, and then we're going to have a pi bond, which we're going to talk about at the end of this video. And that's what's going to form the second bond between these 2 carbon atoms. So here I want to briefly mention how we expand octet. So for those elements that are in the 3rd period or below, which we learned in a previous video, that can expand their octet, how they can do that is typically they have d electrons, and those d electrons are going to be used to accommodate more than an octet around the central atom for hypervalent compounds. So now let's talk about the difference between single bonds and double and triple bonds. Well, how do we make a double and a triple bond if hybridization doesn't really explain how we could make a double or a triple bond? Well, there are 2 types of bonding pairs that we have. We have a sigma bond and we have a pi bond. A sigma bond is head-on overlap between orbitals. So if we had something like 2 spheres for hydrogen, we're going to have sphere-sphere overlap. That's head-on. That's going to be a sigma bond. You must form a sigma bond before you can start to form pi bonds. Pi bonds are when you have p orbitals, and the p orbitals have that dumbbell shape, and then the sides of the dumbbells are going to overlap. So where you're going to have like this network, a circular shape, but that's counting as 1 bond. So you got to start thinking about these in 3 dimensions. So if we have something like propene again, we're going to have to form a sigma bond, head-on overlap, before we can form a pi bond or a double bond. All single bonds must be sigma bonds, and then any second or third bond would then be a pi bond with that p side-on overlap. So knowing the difference between a sigma bond and a pi bond is going to be important when we start to talk about resonance. All the sigma bonds are localized, which means they're staying in that locality. So for something like our propene again, all of our single bonds are localized and those electrons stay there. Propene doesn't resonate, but if it did, only the pi electrons or the p orbital electrons are going to be the ones that are able to resonate. So if we're to look at this diagram here, the resonating electrons in benzene, these 3 double bonds that can shift among 6 different positions, those all have to be pi bonds. So we would have 3 pi bonds in benzene here, and all the rest of the bonds would have to be sigma bonds, localized electrons. So there it is, you guys. There's the video on shapes, polarity, hybridization, and the idea of sigma versus pi bonds. So if you like this video, smash the like button, subscribe, send it to your favorite goblin, send it to your favorite magician, and we'll see you in the next video.